Did you get it right?
Oh, thanks a lot.
Okay, let's get started.
Yeah, so sorry for the technical issue. It's a great pleasure to be here to speak about joint work. It's actually a joint talk with Anand on formalizing Gardam's disproof of Kaplansky's unit conjecture. Though it's called Kaplansky's unit conjecture, this actually predates Kaplansky by a couple of decades. Okay, so history is a bit complicated. It's a very important basic question, and it's one of a whole host of conjectures, some of which are algebraic in nature, some in topology, some in K-theory. And in some sense, this is the first of them to be disproved. It's important enough that in courses I have mentioned this more than once. So it's remarkably short paper, so it's nice to formalize. Gardam disproved this about 2 years ago. I'll spend quite a lot of time just explaining the basic mathematics. So part of the reason is that, well, otherwise things won't make sense, but part of the reason is a lot of the thing in work in formalization was just correctly setting up the mathematics. Okay, so this was done in Lean 4, and one of the motivations of doing this at all is it's a mixture of computation and proving. And Lean 4 is a programming language as well as a proof assistant and even a meta-programming language, so that was not relevant here, all integrated with each other. So it's very well suited for doing this. Of course, there are other ways of doing it, but it's pleasant doing it in Lean 4. Okay, so what is Kaplansky's unit conjecture? I'll start with some fairly basic stuff to motivate this. Well, you know that the product of two numbers is 0, one of them must be 0, but if you're looking at pairs of numbers, this is not true any longer. 1, 0 times 0, 1 is 0. So these are called zero divisors, things which divide 0, you multiply and you get them. And this concept makes sense in a ring, which is a set with addition and multiplication, addition forming a abelian group, and multiplication distributing over addition, but numbers need not have inverses, multiplicative inverses, and the multiplication need not be commutative. So a ring has 0 divisors if two things multiply to 0. 0 here is the additive identity. Okay, unit is something which has a multiplicative inverse. For example, in integers the units are 1 and minus 1, and n by n matrices, it's not hard to see that units are exactly invertible matrices, and 0 divisors are all other matrices, in fact. So commutative ring is a field if every non-zero element is a unit, like rational numbers or real numbers, and so on. Okay. An example which motivates a little better is polynomials. We can add and multiply them, they form a ring. And if you see, if you multiply two polynomials, the coefficient of the highest degree term is the product of the corresponding highest degree coefficients. So you can immediately conclude from this that if two polynomials multiply to 0, then one of them is 0. And if two polynomials multiply to 1, that is, they're a unit, then they both must be constants and non-zero constants. Okay, all this holds for any field. You can change your coefficients to, instead of real numbers, rational numbers, finite fields, etc. Even better motivation are Laurent polynomials. Here we are allowing negative powers, so it could be 3x plus 2 by x squared is a Laurent polynomial. So any Laurent polynomial is of this form, ai x to the ni, where ni are integers, and multiplication extends x to the n times x to the m is x to the n plus m. Okay, so again we take ai to be elements of any field. Again there are no 0 divisors. Again you will look at the higher term. What about units? There are a few more. If I look at ax to the k, then 1 over ax to the minus k is going to be a unit here. But these are all the units. It's a simple exercise, not completely trivial for, say, an undergraduate, but these are all the units. Okay, all this motivates Kaplansky's conjecture in a minute. What we want to study are something that generalize this, group ring. So this is the vector space. If we have a field k, we look at the vector space with the elements, with basis being the elements of G. So an element of this group ring is a sum, ai gi. So this is just like Laurent polynomials, ai x to the I, ni, but I'm just taking elements in an arbitrary group. And the multiplication on the group by linearity will give you a multiplication on the group ring. This is the simple definition. And in fact, Laurent polynomials are a special case of this. If you take x as the powers of x, that's a multiplicative group of integers. And so you get this as the ring of Laurent polynomials. Okay, just now we were talking about units with Laurent polynomials. What happens in a group ring? Well, suppose G is a torsion element in a group. That is, G to the n is E for some E. In a finite group, every element is a torsion element. Then we have zero divisors by this simple calculation. 1 is the unit in the ring. 1 minus G into 1 plus G plus this is 1 minus G to the n, which is 0. Okay. Now, what about units? Well, there are units, A times G is a unit, like in Laurent polynomials. But most groups with torsion, for most groups with torsion, K of G has non-trivial units if G has torsion. There are a few exceptions to this. Actually, zero divisors are used to construct these units. These two are closely related to each other. That's why I've introduced both of them. Statement is a little more complicated. But so if we have torsion, we have zero divisors, and usually we have units. So what did Kaplansky conjecture? Actually, Higman's work is before Kaplansky conjectured this. So as I said, what Kaplansky was not the first to conjecture this. But if the group is torsion free, then Kaplansky's unit conjecture says there are no non-trivial units. So that torsion is the only source of non-trivial units, and the zero divisor conjecture says it has no zero divisors. Now this is actually very important in mathematics. It's related to topology, Reidemeister torsion and so on, K-theory, etc. There is another meta reason why this is a rather interesting set of conjectures. It's because we have to somehow use the hypothesis the group is torsion free. And there are many statements in topology particularly where the hypothesis is that a group is torsion free, and we have not been able to prove or disprove basically any of them. There's Whitehead conjecture and so on. So these are, It's a very important set of conjectures, Kaplansky's conjectures. A couple of years ago, Gardam proved the following. So he considered a specific group, we will call it Gardam's group. It was known to be torsion free, and he took a field with two elements and showed this as non-trivial units. So Kaplansky's conjecture, after many decades of remaining open, was shown to be false. Interestingly, there was computer assistance in a different sense. He found the units using a SAT solver. So mathematical work was done in choosing the group and various other things. It was actually a SAT solver that was used. Now, a couple of weeks ago, Gardam actually proved this for C, the field C, which is more important, that over complex numbers also you have units. Again, using a computer to find that. We haven't yet formalized this, but let me just make one quick comment. The gap additional thing we need is deciding equality for algebraic integers. The reason I'm saying algebraic numbers. Okay, the reason I'm saying this is because some of you may be experts in that kind of thing. It is much worked on problem. Okay, there are algorithms for this. Okay, so now some more mathematical background. Fix a type B for basis. Okay, so we have to construct vector spaces. I'm going to talk about the background and formalization together. We have to construct a vector space over K with basis B so that we can decide equality on V. Okay, so that is, the decision problem is solvable, and the basic property of vector basis in linear algebra holds true. That is, given a function on the basis B to a vector space W, we can extend it to a linear map. Okay. And once we have this, what we can do is take the basis to be the element in the group, and you get an underlying vector space. And by linear extension, we can define the multiplication. So this is how we are going to construct vector spaces in group rings. So something about Gardam's group, as I was saying, very well understanding this group, choosing what treatment to use of it, choosing the level of abstraction, all these were crucial in the formalization going smoothly. Okay, so we need to construct the group, we need to show that it's torsion free, and at the same time we need to decide whether two elements are equal or not. Okay, Gardam gives lots of examples, descriptions of this group. I mean, they've been known for a while. It's in fact a three-manifold group, it's a crystallographic group, gives the description generated by matrices and uses this with gap, etc. But for us, what turned out to be the best was a description as a meta-billion group. I'll say what meta-billion groups are. This worked very well for both the goals. Okay, so these are group extensions We could have tried to formulate, we did formulate it as group extensions, but on the other hand, we didn't do it in full generality. These are particularly simple cases. So right through, we kept making choices whether to be more abstract or more concrete, and each case depending on what was easier. So using group extensions was nice, but also using the simplification. So these meta-abelian groups are one step away from abelian. So there are groups which have an abelian subgroup, which is normal, and the quotient is also abelian. So obvious examples are products, and anyone who has seen groups has seen one example of a meta-abelian group, S3, permutation on 3 letters. It has a cyclic group of order 3, which is the 3 cycle, and the quotient is odd and even permutations, which is Z mod 2Z. Okay, so this is not abelian, so it's not a product. And the group G equals Z can be viewed also as a meta-abelian group if you are perverse enough. It's of course a product, but we'll take K to be even integers, and then the quotient is Z mod 2. It is not this product, and it's not this product because it's not split. Now the great thing about this is exactly the 2 ways a group can fail to be meta-abelian. So a meta-abelian group is determined by K, Q and 2 obstructions. In English, obstruction means difficulty, but in algebraic topology it doesn't. It means data. And data is good for us because we are working on a formal proof system or programming. You want data. So here's data giving you a meta-abelian group. You're given K, Q. Okay, let this be the quotient homomorphism. So because K is normal and abelian, conjugation gives a group action of the quotient on K. Okay, because K acts trivially on itself. This is one piece of data. It measures how you're not abelian. The action is trivial if you're not abelian. Not being split is measured in a different way. Let's take a section, as it is called, a map from Q to G, okay, which is a set-wise inverse only. If this is a homomorphism, the group is split, so let's measure how much it fails to be a homomorphism. So if S of Q1 into S of Q2 is S of Q1, Q2, it's a homomorphism. We measure how it fails to be a homomorphism. The fact that our group is associative gives you a co-cycle condition. Co-cycle modulo co-boundary, whatever that is, doesn't matter to us, is exactly the obstruction to being split. But what is relevant for formalization is that KQ, 2 pieces of data, a group action and this function satisfying a co-cycle condition is the data. Namely, if we are given Q and K and a group action, we construct a meta-abelian group structure, and here's an explicit formula. Okay, and we have to prove that it's a group. The hardest part is associativity. It comes from the co-cycle condition. How about the concrete group we want, P? We take K is Z3 and Q is Z2 cross Z2. And the group action and co-cycle, Gardam's paper has explicitly, they have been known for a while. And we verify that these are a group action and co-cycle, and we have got B. Now we want to show also this is torsion free. Note that K itself is torsion free, that's pretty trivial. And since Q is 2 torsion, the square of element in every element is in K. So if I take a torsion element, its square is torsion, so and is in K, so it must be 1. So all we have to show is that if a torsion element if an element square is 1, then G itself is 1. We do this by considering cases. Okay, so a few words on the formalization. So Gardam's theorem has 2 components. It's torsion free and it has non-trivial units. First is largely a proof and second is largely a computation, though both involve an interplay of both. And we are not using anything untrusted here, meaning we are working within Lean, which is both a programming language as well as a computing proof. Okay, and the definitions should be suitable for both proofs and computations. So computations give proofs via decidable type class. Okay, so decidable type class, so given a proposition, decidable P is either a proof that it's true or a proof that it's false. For one proposition, this isn't much. For a family is where it will become more interesting. And the fact that this is a type class means there's automation called type class inference, which can provide this free for you. So we solve decision problems, which is implementation of instances. And we also do our own type class inference to do enumeration. And not just that, for linear maps, enumeration over a basis. Okay, then we use native decide or decide to give the proofs using these. Okay, so free modules, they generalize vector spaces. We define free modules over a type. So all we do is we look at list of A cross V and take a quotient of this type. Okay, so the way we take the quotient is we can look at coefficients and the lists are equivalent if they give the same coefficient. We have to take equivalence because, for example, the order in the formal sum that doesn't matter. It gives you the same element. Okay? And it's easy to derive decidable equality from these. You need a finite support condition. What you can't do easily with this definition is prove the what's called universal property. So instead we show that two lists are equivalent if and only if the elements are related by elementary moves. And from these we can conclude the property that functions on B extend to homomorphisms on the free module, and this lets us construct the group ring in 2 steps. Okay. Final comment about this before turning to the group. The main failure point with such a formalization is what if our definition was wrong? What if what we defined was not the group ring at all? So as additional checks we prove certain properties, even though all I've said so far is enough for our proof. We proved that that ring is a ring, so we have to prove associativity, all sorts of other properties. We also showed that there are some natural functions, inclusion functions from R and G to R of G, that these 2 functions are injective. Incidentally, the second test was suggested by Gardam, who we spoke remotely in London Learns Lean, so we were here, but we were not here, and he was in Germany too. And so he suggested this, so we proved this as another test. Yeah.
Am I audible? So as we've seen, the proof involves both a proof and a computation. And it turns out that the definition of the group P is common to both these parts. So it becomes important to choose a definition of P in a way that's suitable for both of these. And the proof of torsion freeness requires being able to peek into the structure of the group carefully and analyze the elements, while the computation requires being able to check equality of elements efficiently. And the group P has various definitions. Some are better suited for one purpose, some are better suited for the other. But the definition that we finally settled on after considering various possibilities is the definition of P as a meta-Abelian group, which turns out to be useful for both these purposes. So we've seen already that given 2 abelian groups, K and Q, we can define a meta-Abelian group by 2 pieces of data. One is a group action of Q on K by group automorphisms, and the other is a certain map from Q times Q to K called a cocycle. And once we have these 2 things, we can construct a meta-Abelian group, and we can construct the group P by specializing this construction with the appropriate cocycle and group action. So for that, we need to define the appropriate components, and these more or less follow the definitions on paper once one is used to the notation. Now finally, to construct a meta-Abelian group, we can, given an action and cocycle, we can explicitly do this on the set K times Q with an explicit formula for the multiplication, the inverse, and the identity. We also need to verify formally that with these operations, the structure forms a group, and we can use the Aesop tactic for this. So here are the definitions. Here's the multiplication in the group. It's given by this formula over here, the identity, the inverse, and here are a few of the relevant checks. As we can see, the Aesop tactic, which is one of Lean's automation tactics, makes short work of this. All the proofs are 1 or 2 lines long. The proof that multiplication is associative is slightly longer, which is why it's not on the screen here. But rest assured that it's not too difficult either, and it follows from the cocycle condition. And so finally, this sort of concludes the construction of meta-Abelian groups in general, and we finally need to construct group P by specializing with the appropriate cocycle and group action. And since we're doing things formally, not only do we have to specify the maps, but we also need to give the formal proofs of the various properties. And this is a bit tedious to do because it's a specific proof about a specific object, which can be really tedious to do explicitly. But we instead approach this via automation, by proving relevant lemmas to specialize down to the finite and computable setting, and finally automating these using decision procedures and type class inference. So here are the components of our group. So that's the group K, which is Z cube. This is the group Q, and here is elements. And here are the explicit maps for the cocycle and group action. So that's the group action, that's the cocycle. But in addition to these bare maps, we also need to prove the various properties, which can get a little tricky, but we have a way of getting around this. So to show that the group action is in fact a group action, we need to decide equality of homomorphisms. And these homomorphisms around the group Z cube. So equality just by enumeration isn't feasible, but we use the fact that Z cube is a finitely generated free abelian group on a basis of 3 elements. So verifying equality of homomorphisms is in fact just equivalent to just verifying equality on the basis. So that's just enumeration, which we can handle by type class inference and decision procedures. The cocycle condition is a little trickier. So while it's a finite problem, it involves a case check of 64 cases, which is completely infeasible to do by hand. But this is an iterated enumeration over a decidable problem, and we prove relevant lemmas to sort of bootstrap and synthesize an algorithm for this through type class inference and previously established general decision procedures. So once we've set up the background for this, verification actually turns out to be not too hard. So this in total is the verification that the group action and the cocycle are in fact maps that satisfy the properties. And now we can define the group P as a metabelian group. And with the group P defined, we turn to torsion freeness. It's more or less the same as the mathematical sketch we've seen earlier, so I'll be brief here. So we need to show that given an element in P, its square lands in the kernel K. Lead is a language that has types, so this has to be stated a little differently. We first define a map, square, which sends an element of P to an element of K. And then we show that if for any element in P, its square matches with this function over here. So that's an abstract way of stating it. We also need to show that the kernel is torsion free. So the kernel is Z cube. So it's sufficient to show that Z is torsion free and that the product of two torsion free groups is torsion free. And once we have these two facts, this can be established by type class inference. So it's a single line over here. And we also need to do a certain general calculation in a group, which amounts to showing that if you have a torsion element, then square is also a torsion element. This is a really simple calculation, which we see on the screen over here, a couple of lines long. And so far, what we have is that we need to show that the group P is torsion free. And how we do this is by taking an arbitrary torsion element of P, squaring it so that it lands in the kernel. But we know that the kernel is torsion free. So that means G square is actually the identity. But it turns out that in our group, if G square is the identity, then G is itself the identity. And we establish by proof on cases, and that automation handle this. And together this covers the proof that P is in fact a torsion-free group. Now we've covered most of the components. We know that we've constructed the group P, we proved that it's torsion-free, and we've established the machinery for group rings. So verifying Gardam's result is a trivial computation now. So here are the two units from Gardam's paper. They're defined in terms of polynomials P, Q, R, and S. We need to show that the unit is non-trivial. So we first define what it means to be a trivial element, which means that it has a unique non-zero coordinate, and we show that it's non-trivial by exhibiting at least two different coordinates on which it's non-zero. And finally, we need to show that it's a unit. So for it to show that it's a unit, we take the unit and its inverse and multiply them together to show that the result is 1. So unfortunately, this is a little too complicated for kernel reduction, but native decide is able to do this fairly quickly. And so this is where our group ring machinery comes in, and we show that this is a unit. Finally, we state the unit conjecture over here, and we show that the unit conjecture is false by putting everything together. And this is our verification of the result. Like Siddhartha mentioned, we also need to do a few verifications to make sure that our formal definition matches with the definition on paper. And here are a few things we prove. For example, a few things about group rings that we've seen already. And we also need to show that, for instance, our definition of a non-trivial unit matches with another mathematical description which is independent of our implementation. And a metabelian group satisfies its defining short exact sequence. And with that, I'd like to conclude. So this was our formalization of Gardam's disproof of Kaplansky's unit conjecture. And it involved a mix of proofs and computations. And it was also an instance of a real-time formalization of a mathematical result. These are becoming increasingly common, especially in areas like combinatorics, and hopefully they'll become even more common with time. And I'd like to end here. We're happy to answer questions.
Right. Thanks for the wonderful talk. So if you have any question, again, use this microphone with your name and affiliation.
Hi.
Yeah. All right. Yeah, sure.
Hi. So I'm Mevin Lindon-Bertrand from the University of Cambridge. I have a question about the whole decidable setup, because that's something that's very natural to do in these like constructive proof assistance. For instance, MathComp and Coq relies on this machinery a lot. But I'm surprised of seeing people using this in the non-constructive setting, because I think that everything is decidable in Lean because you have excluded middle. So is it that you know? Am I wrong about this? Or is it that you only consider like the something to be decidable if you have a completely computational witness that the thing is indeed...
Here what we are doing is... Oh, I don't know. Is it not? Oh. Yeah, okay. Sorry. So the point is that, no, so there are two different things. Yes, logically, if we include the law of, incidentally, we do not, in our work, we did not import classical. Oh, so nice. We did not use the law of excluded middle. But that's not the important point. Yeah. The important point is that we are not really concerned about the logical status of decidability. Yeah. If we actually have a decision procedure implemented, okay. Yeah. So Lean has things that are non-computable and computable. Yeah. So nothing in our case was non-computable. Okay. They were all computable. So if you have a decision procedure, you can just run it and decide using that. Sure. So we had computable definitions. Yeah. So while Lean does allow law of excluded middle and make things non-computable, so if we try to use the decide tactic, there is a tactic called decide, which will run. If you made something non-computable and ran the decide tactic, you would get an error. Okay, I see. So there is so with Lean 4, the choices are not made, and this was a great convenience for us. So we can work on at the existential level or at the concrete level, and we can lift from concrete to existential level. We better not be able to do it the other way, but we can't, and so this non-computability versus this makes things work perfectly fine. Okay, thank you. Thanks.
Hi, thanks. So you mentioned Hickman's theorem along the way.
Yes, yes.
And so I wanted to ask whether it's formalized or if you're planning to formalize it.
The Hickman's about existence of units.
Yes.
Well, we haven't really... actually, I think that's not one theorem. That's the problem. I think it's not difficult to formalize. When we are going from zeros to units, there are many constructions. So this was Hickman's thesis. So we'll have to formalize many constructions. We didn't have any immediate plans for that, but yeah. I mean, it's a nice formalization exercise. It is to show that there exists unit if we have torsion. I mean, the other one we can formalize in just a few minutes, maybe. That is to say that if you have torsion, then you have zero divisors. I think anyone experienced in any proof system could probably do it in an afternoon or something like that. Hickman's is interesting because it's many constructions. Yeah. Of course, what is really interesting is maybe Gardam's proof over C, because that's a major mathematical result. And yeah.
Anyone else have questions? Okay, I have one more. So are you planning to formalize the new proof with the complex numbers?
Yeah, so certainly, I mean, in fact, I was going to ask on Zulip about this. So the difference between the two is that in the finite field, it is trivial to decide whether two elements are equal or not. So in the new proof, what you have is you have a certain field which is not finite. It's a finite extension of Q. And given two elements of this field, we want to decide whether they're equal or not. Now, it's well known that even for algebraic numbers, there is an algorithm to decide equality. But so far as I know, there is no implementation yet in Lean, and I think this is something which would be very nice to implement in Lean, that is decide equality. But maybe someone knows if someone has implemented or is about to implement it. So there's a completely separate thing we have to do, which is would be useful. And given that, we just plug in different numbers. The rest of the code is almost identical to this. So yes, certainly I would like to do that, because I think because I would like decision procedure for algebraic, at least for some fields, for algebraic numbers to be part of Lean. I think it's part of the spirit of Lean 4 that we just use decision procedures where they're there. But yeah.
Okay, thanks. Your last chance. All right, then let's thank the speakers again.